All right. How are you guys doing? This is the exam to review solutions. They ask you to now be careful. It's not about can you do these exact problems. But it's do you understand the concepts and what it takes to do these problems. That's going to get you a good grade on your test. So we'll roll through these, and if you have more questions, just let me know. Shoot me email, whatever, and we can make an appointment and meet up for sure. All right, graph the following systems of equations. So I'm going to do the first one, and it's going to be easiest for me. I'm looking at this is to go, oh, let me just make a quick little table because I know they're lines. If x is 0, y is 4, and if y is 0, x is 2. So 2. So x and y, so 0, 4, and 2, 0. And since it's equal to, it's a solid line. Which way do I shade? Well, I'm going to plug 0, 0 in. 0 plus 0 is in fact less than 4, so I know I'm going to be shading this way. Include the point including 0, 0. Now on this one, I'll do the same thing. If x is 0, y is 3. And if y is 0, x is 9. So that's going to be this guy here, 0, 3, and 1, 2, 3, 4, 5, 6, 7, 8, 9. And since it doesn't equal 9, it doesn't include the line, so it's going to be a dotted line. And if I plug 0, 0 in, 0 plus 0, 0 is less than 9 for sure, that's true, so I'm going to be shading down. So the double shaded area is the solution, which is going to be all of this. Let's just go with yellow. Right? Do you guys see that? So it's all this region down here. It goes on forever both ways, or forever that way, right? Okay, graph the following, graph these. So again, I'm going to just do, if x is 0, y is 5. And if y is 0, x is 5. And it's a solid line because it's equal to here. And if 0 plus 0 is in fact less than 5, so I know I'm going to shade down. X minus y is greater than 3. So if x is 0, I'll have 0 minus y is greater than 3. So if I divide by negative 1, don't forget it switches direction, right? Although I'm not really looking at that. Sorry about that. Forget that. So for here, let's just do this, x and y. If x is 0, remember I'm assuming they're equal. Y is negative 3. And if y is 0, x is 3. So for the second equation, I've got 0, negative 3, and 3, 0. And it's dotted line because it's not equal to. If I plug 0, 0 into it, 0 minus 0 is 0 is greater than 3 is false. So I'm going to be shading this way. And then I've got x is greater than 1, so x equal 1 is this line right here. And x is greater than 1 is all of these this way. See, this starts to get a little bit messy, so you got to kind of be careful to see where's my triple shaded region. And then I've got y equals 3. Well, y equals 3 is up here. And it's going to go like y equals 3. And y is less than, that's going to be shaded down. So I'm really only interested in the triple shaded area. So that's going to be here, right? Here. that region, okay, because I am coming down this way on these, right? So now it's my quadruple shaded region. So it's to the right of the gold, below the orange, below the red, below the green. So there we go. Okay, find maximum minimum value subject to these constraints. So for a problem like this, I want to graph and find my feasible region and then find the corner points. So this is not going to be nice, because if x is 0, y is 9, but if y is 0, x is 9 over 2, or 4.5. So 0, 9, and 4.5, 1, 2, 3, 4.5. That's equal to, and 0 plus 0 is 0 less than 9 is true, so it's going to be shaded down. Now, why am I only shading the first quadrant? Because I looked ahead and saw that, oh, x and y are 0. If x is or greater than 0, if x is positive, that's this way, and if y is positive, that's this way, so it's only the first quadrant. So I'm going to try to keep my drawing a little bit neater. Then I got 4x plus 3y equals 23. So I've got x and y. So if x is 0, y is 23 over 3. Oh man, so it's 7 2/3. And if y is 0, this is like real life though. X is 23 over 4, which is 5.75. So I'm going to have 1, 2, 3, 4, 5.75. 0, and then 0 and 7 2/3. 1, 2, 3, 4, 5, 6, 7 2/3. Again, that's a solid line. And 0 plus 0 is greater than 23 is false, so I'm going to shade the other way. Ooh. So I'm shading up. So my triple shaded region is right here. And to find the maximum and minimum values, I got to figure out what are these coordinates here, here, and here, right? I'll put them in red. Well, I know this one, because that's from the first one, that's 0, 9. And this one is from the green line, which is 0, 7 2/3. And now I got to find where they cross. So where do these lines cross? 2x plus y equals 9. 4x plus 3y equals 23. I'm going to multiply this one by -3. You get -6x minus 3y, because then my y's cancel. -27, so I get -2x, those gone, equals -4. Oh, that's nice. So x is 2, and then that makes y equal 2. I can plug it into either one of the equations. That'd be 2 times 2 plus y equals 9. 4 plus y equals 9. So y must be 5. So that's the point 2, 5. Okay. So I want to find the max and min for z equals 2x plus 5y. And I've got the point 2, 5, 0, 9, and 0, 7 point, 2/3 is 6, 6, 6 repeated, so 7.67. So then what is z going to get me? So here z equals 2 times 2 is 4, plus 25 is 29. Z equals 0 plus 5 times 9, which is 45. And here z equals 0 plus 5 times 7.67, which I will do on my calculator. 7.67 times 5, 38.35. So there's my max at the 0.09, and there's my min at the 0.25. Okay, so there we go. That one's, you find the big picture, find the feasible region, find the corners, and substitute them into my objective function. Go from there. Okay, so these are the same things. This is the same type of problem, only now we're going to apply it. And this just says write the constraints. We don't have to actually solve it. So the Twin Ivies Theater has a seating capacity of 275 adult tickets, children's tickets, ticket sales of at least this to break even, write the constraints. So we got to identify our variables. So we're going to say X is the number of adult tickets sold. Y is the number of children's tickets sold. And we want to just write the constraints. So the capacity is 275, so X plus Y has to be less than or equal to 275. Adult tickets sell for this, and we want to sell at least $1,100. So $7.50 times the number of adult tickets plus $4 times the number of kid tickets has to be at least 1,100 because we want to break even. And we certainly know that you have to sell positive adult and positive kid tickets. So there's my constraints. All right, and what they're probably going to ask is what's the maximum profit, but they didn't ask that, so we don't have to worry about it right now. Okay. 18 suits and dresses, 1 yard of material. What restrictions on the number of suits and dresses? So let's X equal number of suits made, and Y would be the number of dresses made. I learned the other day when I actually went with my wife to a store, I don't know, Joann's Fabric. We bought fabric, that when you buy a yard of polyester, that doesn't mean a square yard, that just means a yard of length, depending on whatever size the roll is. It's just 3 feet of it. And I did have the person that was working there clarify to me that there is in fact 3 feet in 1 yard. And I restrained from saying anything else. Okay, so what are our constraints? A suit requires 1 yard for of each dress. Taylor has 80 yards of polyester and 80 yards of wool. Okay, so how much polyester that we have to be less than or equal to 80, right? So how much polyester do the suits need? Well, the suits needs 1 yard. So 1 yard times the number of suits. And the dress is 2 yards of polyester, so 2 times the number of dresses has to be less than 80. So this is the polyester. And then the wool, well, a suit requires 4 yards of wool, so 4 yards times the number of suits plus 2 yards for a dress times the number of dresses has to be less than or equal to 150, because that's all we have. And we know that X is positive and Y has to be positive as well. All right, there's my restrictions. Okay, so we want to set up the problem but don't solve it. Southside Landscapes proposes to plant the flower beds for the historic Earl House Gardens. Company uses 4 patterns and it tells us stuff about each. I kind of want to get to the end to see what I'm finding. How many of each pattern should be used to maximize profit? So we've got let's let X1 be the number of pattern 1. X2 will represent the number of pattern 2. x3 will be the number of pattern 3, sorry for writing so sloppily. And pattern 4, x4 will represent the number of pattern 4, and that's it, right? Okay, so now we want to maximize profit. So profit P. So do we know what the profit for each pattern is? 48 for pattern 1, so 48x1 plus 45x2 plus 55x3 plus 65x4, right? That's my profit, so that's what we're trying to maximize. Now my constraints. I know I have to have positive constraints, so x1, x2, or positive constraints, positive number of patterns. Okay, now I got to go back and read through this and see, okay, what do I have? What are they telling me, right? Tells me how many tulips, daffodils, and boxwood I have. Pattern 1 uses 40 tulips, 25 daffodils, 6 boxwood. 2 has these. See, sometimes you just have to read through it a bit to figure out, okay, what am I given? What are we going for? Well, it looks like we have total numbers of tulips, daffodils, and boxwoods available, and it tells me how many each pattern uses. So if I have pattern 1 uses 40 tulips, so that'd be 40x1, and then pattern 2 uses 25 tulips. Pattern 3 uses 30 tulips, and pattern 4 uses 45 tulips. And that's to be less than or equal to 1250. These are the tulips. Then we got the daffodils, and then we got the boxwood. Okay, so daffodils, pattern 1 uses 25, pattern 2 uses 50, pattern 3 uses 40, right? See where these are all coming from? Pattern 4 uses 45. And that has to be less than or equal to 1600, because there's only 1600 daffodils. And then boxwoods, how many boxwoods? Pattern 1 uses 6. Pattern 2 uses 4. Pattern 3 uses 8. And pattern 4 uses 2. And that has to be less than or equal to 195. So there are my constraints that I have to satisfy, and then I want to figure out what values of x1, x2, x3, x4 make this the maximum. Okay, I'm going to stop this one there, and we'll pick up on part 2 on the next video.